Hi everyone. In the last class, we have discussed about spectral properties of an element in a Banach algebra and the spectral radius formula. So today we will discuss about ideals in a commutative Banach algebra. Okay. So let us look at the definition that A be an algebra and I is subset of A, then I is called an ideal if I is a linear subspace. Second one is I is an ideal in the ring A. So that is whenever A in A and C in I, this should imply that AC and CA both should be in I. So this is a definition of an ideal. So we say I to be maximal to be a maximal ideal if I is an ideal I not equal to 0 and I not equal to A, and if J is any ideal, any other ideal such that I is contained in J, then J must be equal to I. If this condition is satisfied, then we call I to be a maximal ideal. So let us see a few examples of maximal ideals. And ideals. Let us take A to be C of K, the space of all continuous functions defined on K and taking values in C, where K is compact Hausdorff space. Okay. Let us take F to be a closed subset of C. I will define I suffix F as set of all F in A such that F of t equal to 0 for every t in F. That means set of all functions F in A such that F restricted to capital F is 0. So we can easily check that this is an ideal. It is easy to verify that I suffix F is an ideal in A, and it can be shown these are the only ideals in A. If I is an ideal in A, then there exists a closed subset F of C, F of K such that I is nothing but I suffix F. That means these are the only ideals in A. And one more thing, we can easily show that if F is a singleton set, then we can show that if is maximal, and the converse is also true. So we can easily verify, show that all the maximal ideals are of the form I equal to I suffix f, where f is a singleton set. Okay, so these are the ideals in C of k and ideals in maximal ideals in C of k. So let us look at another example. Okay, so let us take a equal to mnc, n bigger than or equal to 2, and define d as set of all aij such that aij is 0 for all I not equal to j. Set of all n by n matrices which are diagonal. Then we can easily show that D is a subalgebra, but not an ideal in A. Okay, so these are the few observations about ideals. So if we have a homomorphism between two algebras, so let us look at definition. Let A be unital algebras and phi from A to be a map, then phi is called a homomorphism if phi is linear. So that is phi of A plus alpha B is phi of A plus alpha phi of B. So this is, and phi is multiplicative. Phi is that is phi of AB is phi A multiplied by phi B. So if AB are normed algebras, then phi is called an isometry if norm of phi of A is exactly norm of A for every A in A. Okay, so we say phi to be a homomorphism if phi preserves the linear structure of A as well as multiplicative structure of A. That means phi preserves the algebraic structure of A. Okay, so it is easy to show that if phi is a homomorphism, then kernel phi set of all A in A such that phi of A is 0 is an ideal in A. So this is easy to show. That means kernel of a homomorphism is an ideal. Okay. So if phi is homomorphism, then we can show that phi preserves the invertible element. Next, we can say that if phi maps unit element into unit element, then it sends invertible elements into invertible elements. So let phi of 1a equal to 1b, then phi of Ga is contained in Gb. So let us take an element A in Ga, then there exists unique B in A such that AB equal to BA equal to 1A. Since phi is multiplicative, then we can say that phi of AB equal to phi of BA, that is phi of 1A, or we can say that phi A phi B equal to phi B phi A, that equal to 1 into B. So from this we can say that phi of A is in G of B. So we can say that if phi is a homomorphism, we can conclude that uh, we can comment something about the spectrum of element. So if is a homomorphism, with phi of 1a equal to 1b, then spectrum of phi of a with respect to the algebra B is contained in spectrum of A with respect to algebra A for every A in A. So we can say that both become equal provided phi is a bijection. If phi is bijective, then we can say that spectrum of phi of A with respect to B is spectrum of A with respect to A. So this directly follows from the earlier observation. It sends invertible elements into invertible elements. If uh, so, if we say lambda is not in the spectrum of A, this implies A minus lambda into 1A is in G of A. This implies phi of A minus lambda phi of 1A is in G of B. That means phi of A minus lambda 1B is in G of B. So we can say that phi of A is not, lambda is not in the spectrum of phi of A. So lambda is not in the spectrum of phi of A. This is with respect to the algebra B. Now if phi is bijective, then phi inverse is also a homomorphism. So other way inequality is true. So from that we can conclude that equality holds. Okay. Next we are interested in multiplicative linear functionals. So let us look at the definition. Let A be a unital algebra. So we consider Banach algebra. A functional in fact we consider non-zero functional. A to C is called multiplicative if phi is linear and phi preserves the multiplicative. Phi preserves the multiplication, that is phi of a b is phi of a into phi of b for every a b in a. So let us look at set of all multiplicative elements. So let us denote the set of all non-zero multiplicative linear function by ma. Set of all phi such that phi is non-zero, linear and multiplicative. Okay. In general, 0 is a multiplicative linear functional, but we are not including 0 functional here. So next we want to show that every multiplicative linear functional is uh, bounded, it is continuous, and norm of each function, such functional is 1. So let us have the following observation. If phi is in MA, then phi of 1 into 1, so this is phi 1, that is phi 1 square. This implies phi of 1 is 0 or phi of 1 is 1. If phi of 1 is 0, then phi become 0 functional, but we are avoiding 0 functionals in MA, so this implies phi of 1 is 1. So sometimes we write the subscript as 1a for the unit element, sometimes we don't write it. Okay, so this observation is going to be more useful. So let us look at the following result. We can say that if phi is in MA, then we can say that norm phi is 1. Okay. Okay. So we have norm of phi is bigger than or equal to norm of phi at 1. This is modulus of phi at 1. So this is 1. That means norm of phi is always bigger than or equal to 1. If norm of phi is strictly bigger than 1, by the definition of the norm, there exists some a naught in A with norm of a naught is 1, such that modulus of phi of a naught is strictly bigger than 1. This directly follows from the definition of the norm of phi. Now let us take a as a naught minus phi a naught multiplied by the unit element. Then we can easily show that phi of a is phi of a naught minus phi of a naught into phi of 1, that is 1. So this is 0. So therefore phi of a belongs to kernel phi. Okay, now let us look at, so next consider a naught by phi of a naught, norm of this is 1 by mod phi of a naught. We know that mod phi of a naught is bigger than 1, so 1 by that is strictly less than 1. So this implies, hence we can say that 1 minus a naught by phi a naught, this is an element of GA, that is invertible, because we have shown that if norm A is strictly less than 1, 1 minus a is invertible. Or we can say that phi of a naught minus a naught by phi of a naught is in G of A. This implies that phi of a naught minus a naught is minus a. This is minus a by phi of a naught is in g of a. So from this we can say that a is in g of a. Okay, but we know that a is coming from the kernel, and kernel is an ideal. So if ideal contains an invertible element, it also contains the unit element 1, hence it has to be the full space A, full algebra A. So, so this implies that A is in G of A intersection kernel phi. This implies 1 is inside kernel phi. That is a contradiction, because if 1 is inside kernel phi is nothing but A, or we can say that phi is 0. So a contradiction, because we started with non-zero function. So our assumption that norm phi is strictly bigger than 1 is wrong, hence we can conclude that norm of phi is exactly is 1. Okay. So any multiplicative linear functional which is non-zero must be bounded with norm 1. So let us see a few examples of multiplicative linear functionals. Let us take A to be C of k, where k is compact and Hausdorff. Okay. Let us take x in k. So let us fix this element. So define e suffix x from a into c by ex at f as fx for every f in a. So this functional is known as the evaluational functional. We can easily show that it is linear and it's also multiplicative. So ex fg is fg at x, and fg, the product in ck is the pointwise product. This is fx gx, this is exf multiplied by exg. So this is what we can. So it is easy to show that it is linear. So check that ex is linear. Okay. Let us look at one more example. Let us look at the disk algebra AD. Let us take Z in the unit disk. So define phi suffix Z from A into C by point evaluations for every f in A. So as in the earlier case, here we can conclude that Ez is multiplicative. In the earlier case, we can show that these are the only multiplicative linear functionals. That means if you take any multiplicative linear functional on Ck, so that is given by point evaluation. Similarly, in this case, it is slightly difficult. It is slightly different. You can show that whenever you take z in the closure of D, then also e suffix z, here it is phi suffix z, is multiplicative, and we can also show that all the multiplicative functionals are of this form. Okay. So let us see one more example. Let us take A to be MNC, n bigger than 2. Now we can check that there is no multiplicative linear functional on A. There does not exist multiplicative linear functional on A, because on MNC trace is the only linear functional and that cannot be multiplicative. There are no other linear functionals other than trace. So in other words, if f from A to C is linear, then there exists a matrix X in A such that f of A can be given by trace of Ax for every A in A. So these are the only linear functionals, and we can easily show that this is not multiplicative. That means there does not exist any multiplicative linear functional on MNC. And here this example is very interesting because we can easily show that uh, it does not contain any uh, any ideal inside it. So other than A itself, it cannot contain any non-trivial ideal. Okay. And if you look at the first example, if you look at kernel Ex, that is set of all f such that fx is 0, that is similar to this is exactly a particular case of the kernel of Ex is nothing but uh, the ideal that we have seen here. Ideal I suffix f, where f is a singleton set, in this case it is x, so that will give a maximal ideal. That means in this case here kernel Ex is a maximal ideal. So kernel Ex is a maximal ideal. And if you look at the last example, then since there is no multiplicative linear functional, and we also know that there is no non-trivial ideal, so that means we can guess that there is a connection between maximal ideals and multiplicative linear functionals. Earlier we have seen that kernel of a multiplicative linear function is an ideal, and now we will show that there is a one-to-one correspondence between maximal ideals and multiplicative linear functionals. Okay, so we'll write this as a theorem. So let us look at a Banach space. Let X be a Banach space. Then X star is the dual of X. Okay. If F is a map from X to C, continuous linear and linear, this implies kernel F is a maximal hyperplane. In fact, it is closed. That means X by kernel F is isometrically isomorph with the field C. Now, in this case also, when we have an algebra, if you look at multiplicative linear functional, then we can get a similar kind of result. So let us look at that result. Theorem. Let A be a commutative unital Banach algebra. Then there exists a one-to-one correspondence MA and the maximal ideals of okay. So we can find one-to-one correspondence between the set of all multiplicative linear functionals and maximal ideals in A. So let us look at the proof. So let us take phi in MA. Then we know that kernel phi is an ideal. This we have already observed. We want to show that this is maximal. So the claim kernel phi is maximal. Okay. So let us take an element A naught in A minus kernel phi. Okay. Then look at the algebra. So the algebra generated by A naught and kernel phi. Okay. Now if we can write 1 can be written as 1 minus A naught by phi A naught, because A naught is not in kernel phi, so phi of A naught is non-zero. This is plus A naught by phi A naught. Now this element this is in kernel phi, and this is element in the span of A naught. So we can say that this element is in L. So in fact we can say that every element we can write in this way. So from this we can, so this implies that L is nothing but A. So from this we can conclude that therefore kernel phi is maximal. If this is not maximal, you can find one element A naught in A minus kernel phi. Now if there is an ideal which contains kernel phi, then that ideal should be generated by A naught and kernel phi. But we have shown that such a thing is exactly full space, full algebra, hence this is a maximal ideal. Okay. Now on the other hand, let us look at a maximal ideal and get a functional such that whose kernel is exactly the maximal ideal. Let I be a maximal ideal. We can also show that I closure is also an ideal. We can easily show that I closure is an ideal. So as norm of 1 minus A is bigger than or equals to 1 for every A in A, we know that one norm of 1 minus A is strictly less than 1 implies A is invertible. So for any element in the ideal, we can conclude that norm of 1 minus A is bigger than or equal to 1 for all A in I. We can conclude that 1 does not belongs to I closure. That is, I closure is proper. As I is maximal, so we have that I equal to I closure. Okay, so this is a closed ideal. Now let us look at the quotient algebra. Okay, so let us consider A by I. So let us quickly recall the quotient algebra. Okay. So let A be a Banach algebra and I be a closed ideal in A. Then we define the quotient space as x plus y as x plus yy equal this class. So x is related to y if and only x minus y is in I. So this is the equivalence class set of all y in A such that x is related to y. So if we have two equivalence classes x and y, this we will define alpha x is alpha times equivalence class of x. With respect to these two operations, this is a vector space. Now the product of two equivalence classes is nothing but equivalence class of the product. So with respect to this become an algebra. Now the norm of an equivalence class is nothing but distance between x and I. This is infimum of norm x minus y, where y comes from I. So with respect to these operations, we can say that A quotient I is a Banach algebra. If I is maximal, we can conclude that A quotient I is isomorphic with the field C. So we can, in our case, we have a maximal ideal. So we can get a so so let us take eta from B in isomorphism. Okay. So our idea is to get a functional multiplicative functional phi such that kernel phi is exactly I, the ideal. So define, let pi be the quotient map, be the quotient map, that is A going to A plus I. Now so we have a map from A to C, this is eta, and from A to A quotient I we have pi. So using this we can get phi. So define phi from A to C by phi of A is eta composition pi at A for every A in A. Now we want to show that this is multiplicative and kernel phi is exactly I. So, but we know that both eta and pi are multiplicative. We can conclude that phi is also multiplicative. Now let us look at kernel phi. Kernel phi is set of all A in A A in A such that eta of phi of A is 0. So this is nothing but set of all A in A such that eta of phi of A is A plus I is 0. Okay. Now eta is a map from A quotient I to C. So we can show that this is exactly I. So let me summarize what we have done so far. So we have shown that if phi is multiplicative, then kernel phi is a maximal ideal. So if we start maximal ideal, so then we got phi such that kernel phi is exactly the maximal ideal I. Now suppose phi 1, phi 2 are in MA such that kernel phi 1 is I that equal to kernel phi 2. We want to show that phi 1 and phi 2 coincide. So for that let us take A in A, then we can write B as phi 1 of A minus phi 2 of A multiplied by 1. Okay, so I'll stop here. Thank you very much. Okay, so this can be written as A minus phi 2A minus A minus phi 1A multiplied by the element 1. Now this element is in kernel phi 2 and this is in kernel phi 1, and kernel phi 1 equal to kernel phi 2 equal to I. So on the whole we can say that this is an element of I. So this implies if you look at phi 1 of B, that is 0 because B is coming from I. This is nothing but phi 1 of A minus phi 2 of A multiplied by phi 1 of 1, but we know that phi 1 of 1 is 1, so this is phi 1 of A minus phi 2 of A. Therefore phi 1 of A equal to phi 2 of A, and this is true for all A in A. Hence we can say that phi 1 equal to phi 2.